Okay, let's do some chemistry. Let's do some definitions though first. Matter. This is the physical material of the universe. It's stuff. It's anything with mass and that occupies space. Most of the matter we encounter, the air we breathe for example, the gasoline in our cars, and the food that we eat, consists of a mixture of different pure substances. A pure substance, or simply we just say substance, is a matter that has distinct properties and a composition that doesn't vary. For example, water has always got two hydrogen atoms and one oxygen atom, and it always has the same properties. Table salt is always sodium chloride, sodium and a ratio of sodium and chlorine atoms. Together, they are the primary components of seawater, which is a mixture, and whose saltiness varies from sea to sea. The substance in a mixture retains its own chemical identity and hence its own properties. Whereas pure substances can have fixed compositions, the compositions of a mixture can vary. What do I mean? Well, you can have a cup of sweetened coffee, but it can either contain a lot of sugar or a very little sugar. Our world is a combination of only about 100 very basic or elementary substances called elements. Elements can't be broken down into simpler substances by any chemical means. Now we can do it with a nuclear event, but let's not go there. On a molecular level, an element is composed of only one kind of atom. Atoms are the smallest unit of an element that can exist as a stable, independent entity. Now you may think it's just semantics, but the element kind of describes what kind of atoms there are, what kind of atoms it is. So the atom is the individual, the element is the type. Compounds, well, these are made up of two or more elements in a fixed chemical composition. So water, like I said, is always hydrogen and oxygen, but it always is 2 to 1. Even though there are only about 100 elements, man, there are over 20 million chemical compounds that have been isolated, characterized, and more are coming every day. Let's look at the physical and chemical properties. I need you to understand the difference between these. Physical property, this is the characteristics of a substance, like its boiling point, its melting point, temperatures. Its density, that's the mass per volume, its weight per volume, its volume, its odor, its color. Okay? Chemical properties are just what this substance will do with another substance chemically. It's the reactivity of a substance, like flammability, reactivity with an acid or with water. It is a list of what it can do with other substances. Physical change then just refers to a change in a physical property, like when you melt it or you dissolve sodium chloride in water to make salt water. But a chemical change is more important to us. It refers to that substance totally transforming into a different substance. This is the fun, cool thing about chemistry. Before we can do anything like that, though, let's go back to the basics. And you can't get any more basic than the atom. The atoms are the smallest unit of an element, and they're independent, stable, and they're often called the building blocks of matter. Okay? Atom, as you probably know, has 3 basic components: subatomic particles. Actually, subatomic particles, thanks to those wild physicists, I think they're up to about 200 different subatomic particles. We don't care. We only care about the major ones: the protons, the electrons, and the neutrons. Atoms are really, really small, unfathomably small. We cannot imagine how small they are. They have diameters on the order of 1 to 5, and they get their own unit. This is called an angstrom. It's an A with a little roundy on the top, and it's approximately 0.000000001 inches. Again, you know, I was saying that chemists like to use symbols instead of the entire words for the chemical compounds. Well, we are going to do the same thing with numbers. We're going to use that kind of notation, uh, that 10 to the minus ninth with the superscript. That's going to help us save writing all those zeros. We'll get to that later. What does an atom look like? Well, protons and neutrons are located in the nucleus of the atom. Most of the mass of the atom, how much the atom weighs, is due to the nucleus. That is, the protons and the neutrons together. The electrons are located outside around the nucleus. And most of the volume of the atom is due to these electrons. If you talked about ballpark, okay, a single carbon atom is about 10 angstroms wide. So it takes about 10 to the 10th carbon atoms placed side by side to make 1 centimeter. Oh, stop. That's not right. Never mind. Pause. Take this out. Okay, give you an idea of the makeup of nucleus to electrons. If an atom were the size of Ohio Stadium, the nucleus would only be the size of a marble. But that nucleus marble would weigh 250 million tons. That's dense. Okay. Now, you've probably seen the model of the atom as akin to the solar system, with the electrons being planets revolving around the nucleus. That is old hat, friends, and that is not what chemists and physicists know to be true. What we do now is deal with electrons in a statistical approach. We figure out where they are most likely to be, and then we do a little dot. And you'll notice the dot makes up a beautiful electron, what they call cloud. And it gets more dense near the nucleus, and it gets less dense farther out. But these are not individual electrons. This is just like a sighting, if you will. We don't really know how to measure the electron's path, and it's it's very hard to know what an electron's going to do. So this is a much better representation of an electron than trying to make him a point charge around the center of the nucleus. Okay? Here are some numbers for you. You can't have science without numbers, right? So we've got the particle name. We've got the charge. Notice that protons are got a +1 charge, and each electron has a -1 charge. The neutron, as you might glean from the name, is neutral. The mass, look at these numbers, 10 to the -24. That means that poor number with that negative sign means that there are 24 zeros or 23 zeros before that, because you have to bring the decimal point over 1. So to write that without that number, this little guy up here would be 1. This is how many times we divide this number to get the actual number. So if we did that, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Oh my goodness. I'm tired. I'm not doing that again. So two ways we can do this. We use a system of notation. This is called scientific notation. We'll go into that more detail in a second. Or we make up a new unit, which is what chemists do. This is called the atomic mass unit. And this helps us get to these lovely bigger numbers. You'll notice that the mass of the neutron is approximately equal to the mass, the weight, of the proton. These are the little symbols I'm going to use. Okay, little symbols. This particle, though, is about 1/1000th the mass of the other two. 1 divided by 2,000. Yeah, that sounds good. Of the mass of the other two. This makes them very zippy. They go fast around the outside of the nucleus. Okay, this is the atomic mass unit, and as you might imagine, the atomic mass unit can be defined in terms of grams. Oh, here we go. 1 AMU equals 1.6606, and you can take more numbers out past the decimal point, but I'm not gonna, times 10 to the minus 24th grams. Don't make me do that again. So this is the correlation between these two. This is in AMU units, and this is in grams. All right. These are atoms. Isn't that lovely? So if anybody ever asks you, can you see atoms, you say, you look them right in the eye and say, of course you can. As long as you put, as long as you put quotation marks around C. Because we actually use electrons instead of light waves to illuminate the atoms. And I'm not going there in this class, but these are actual reflections from atoms. You put 250 million of these, you could make the cross section of a human hair. Okay, so let us now look at a cross section of a single atom. And this is just kind of, I mean, this is not saying that I've got a little electron moving. Let's not do that. But let's just use that as the outside. I've got one electron. Sorry, right there. One electron, one proton. This is what we call a hydrogen atom. So all hydrogen atoms have one proton and one electron. It's the number of protons that define the type of atom. For atoms that are neutral, the number of protons equals the number of electrons. They're both got the same numerical charge, just opposite signs. So he's going to be neutral. They've got to be equal. So, carbon atom, what's a carbon atom? Well, it's an atom that's got 6 protons in it, 6 electrons if it's neutral. Why do I keep saying that? Because when we start playing around with the chemistry and putting these together, it's these guys who are going to do all the work. Alright, we never play with protons, i.e. the nucleus, in general, in this class. That's a nuclear event. And they're kind of messy. Chemistry belongs to the electrons. Okay. A gold atom. What makes a gold atom so pretty? It must be the 79 protons, 79 electrons. No. But a gold atom is, by definition, 79 protons. Okay. How do we write this? We use a nice symbol. This is what we call a chemical symbol. And this is carbon. This is the atomic number. He's the number of protons. I'd like this not to say electrons because we are going to manipulate those, so let's just keep it as protons. Up here, this is called the mass number. That's the atomic number. This is the mass number. And he is the number of protons plus neutrons. All right. So for carbon 12, you can write this as carbon 12 also. I've got 6 protons and 6 neutrons. If it's neutral, I also have 6 electrons. Okay. The mass number is given the symbol of A. The atomic number, which of course starts with A, so golly, we couldn't use the letter A. Oh no, we use the symbol Z. And so you'd have the general form of a Z. Usually, atomic number is omitted. And it's because the chemical symbol tells us the number of protons. Okay. If I say he's carbon, he must always have six protons to be carbon. Okay. Isotopes, you can have different numbers of neutrons. In fact, all naturally occurring electron elements have at least 2 isotopes. So if you realize that you can vary these, you've got to figure out a way to take that in consideration. How about carbon? Carbon has many isotopes. For example, we have carbon 11, carbon 12, carbon 13, and carbon 14. What does this mean? Well, let's look at number of protons, number of electrons, and number of neutrons. Woo, this one, 6, 6, 6, 6. Neutral 6, 6, 6, 6. Okay, how about here? 5, 6, 7, 8. They're all differentiated because they've got different numbers of neutrons. Hey, how about this guy? Have you ever heard of carbon dating? Carbon dating utilizes carbon 14 as a timekeeper. As long as we live, as long as biological systems live. So I'm not just including us, I'm including the trees and the amoeba. They take in a little carbon 14. It's radioactive, which means, and it decays. It decays. Half of it disappears. In approximately about 5,800 years. Okay? In a, let's see, how would I say this? In a consistent manner. A consistent manner. So, this means that we can calculate how old a biological thing is, or how long it's been dead, by how much carbon-14 is left. Age determined by how much is left. And this works pretty darn well for an age range of 1,000 to 20,000 years. Beyond 60,000 years, it gets to be pretty iffy, but it's good for this range. Many artifacts have been dated this way.